So the warm-up question, the first one says, what is the polarity of the black end of the magnet? So in the diagram you see two magnets. One of them is black, one of them is white, and we're going to need to determine the polarity, meaning I want to know, is it a north pole or is it a south pole? And we're looking at the black one. So take a moment, look at it if you haven't yet. Okay, so the black end. Again, our field lines always go, which way do the field lines go? Let's start there. When we draw magnetic field lines, we draw them in what way? North to south. Okay, so what is the black end of this magnet? When I ask for the polarity, I want you to tell me if it's a north pole or a south pole. The black end, is it north or south?
It's north.
North, because it's going from the black end to the white end, from north to south. So the black end of the magnet would be the north pole of that magnet. Okay, so that's the answer to number 1. Number 2 says, what direction does current flow through the wire? And you see a diagram similar to the ones we were doing yesterday. And so we're going to look at this one, and we're going to need to use the right-hand rule. So I'm going to bring my screen over here so that we can look at this first question. So I redrew it here so we could see it. But when you're using the right-hand rule, again, in this case, the force is labeled, and there's a wire. So I know I know that this wire is experiencing a force out of the page. So if this was my wire, it's being pushed this way. Okay, but in order for me to determine the direction of the current flow, I need to also know what the magnetic field is doing. And I know what the magnetic field is doing because the magnets are labeled here. There is a north pole and a south pole. We just said in the first question that our magnetic field always goes from north to south. And so although it's not drawn in, we need to add the magnetic field so that we can see which way that field is going. Okay, so that is my magnetic field. So with that, again, we're going to use our right hand. Make sure it's your right and not your left. Okay, and my fingertips represent the magnetic field. The force is my palm. Okay, and so the force needs to be coming up out of the page, so I need my palm facing upward and I need my fingertips facing upward. And when I do that, let me zoom out, my thumb is pointing this way, which is of course to the right. So the current that is flowing through this wire would have to be going in this direction to the right of my page or of my screen. Okay, so again, right-hand rule. This is what we were doing yesterday. I told you that we're going to add some new stuff today with it. Okay, so let's go ahead and go back to the slide. These are the warm-up questions. Please make sure you have answered them in My Open Math, and we're going to get into some notes today with a little bit more on the right-hand rule and applications of it that you're going to see not just today, but tomorrow and the next day as well. You do have a homework assignment, but you're going to have plenty of time to finish it after the notes. So again, I'm going to ask you to hold off on that until then. Okay, so here's just one more example. I have my magnets labeled north and south, and guys, if you see magnets labeled, that means our current carrying wire is traveling through a magnetic field that exists because of these magnets. Okay, we're not looking, if I look at my 2 rules, I'm not looking at, hey, what's the field made by the wire? Okay, I'm not using the first rule, I'm using the second rule. I'm saying, hey, what's the force exerted due to this wire moving through this field? If you see magnets north and south labeled, you're using the second rule. Okay, especially if you see force, especially if it's asking for force. So I know that I'm going to keep my hand flat whenever I do this, but again, I need to draw in my field. There are magnets here. My field has to go from north to south, so that is going to be the direction that I need to point my fingertips in just a moment is going to be from north to south as well, which in this example is going to be toward the left-hand side of my screen. So again, let's go ahead and take a look at this example. So I sketched it here, okay, and we're going to do the right-hand rule. My fingertips need to go north to south, which they currently are, but the problem right now is my thumb. My thumb needs to be in the direction that the current is shown. Guys, what does this X symbol mean?
That is going
going into the page. So my thumb has to go into the page, and this is get really awkward because I'm having a hard time turning my hand like I need to. So I'm actually going to turn my paper. Okay, it's going to make it easier. So my thumb needs to go into the page, and my fingers need to go this way. So my hand is going to look like this. And when I do that, my palm is facing this way. Okay, so I'm going to draw in my force is going this way. Okay, and if I rotate my paper back, that means my force is going upward. I guess I could label my F so that it is correct going this way. Okay, but my force is going upward based on the original orientation of that page. If you need to rotate the page, do it so you can figure out which way it is and then rotate it back and say, okay, that's up. Okay, but that would be the direction of the force on a current carrying wire. If my wire, and if the wire is really going like this, basically, carrying current into the paper like this. Okay, and so the force on that wire, this wire would be pushed upward like that. All right, questions about this? Because if you can't do these easier examples, you're about to run into some difficulty with the ones that are more involved. Okay, so hopefully we're okay with the ones from yesterday. Let's take a look at this. Okay, so here I have a loop of wire. So now my wire isn't just going in one way, it's not a line. It's going to carry current and then it's going to turn around and carry it back out. So it's going to go in right here through this wire, it's going to go down and it's going to go back out over here, okay, as it's labeled in this diagram. And the question says, indicate the direction of the force exerted on the wire. Well, guys, if my current is changing direction, then my force is going to be different in the top of the wire versus the bottom of the wire. Okay, so we need to take a look at what this will look like. First of all, we need to draw in our field. Again, we're talking about determining force acting on this due to an existing magnetic field. So we are using that first rule. But we need to, again, make sure that we draw in the direction of our field so that we can use the right-hand rule correctly. Okay, and so let's take a look at what our force would be in each portion of this wire. So again, I'm going to bring this back over here. My fingertips are B. They need to go from north to south. So my hand is like this. Okay, when my hand is like this, right now my thumb is pointing to the left, which is what it shows down here. So with my hand as it currently is, I'm looking at what's happening to the bottom of the wire. And right now my palm is facing upward out of the page. And so that means the force on this part of the wire is out of the page. The symbol that we use for out of the page is this one. I'm going to label it as a force. So the bottom portion of my wire is being pulled up, because that's what a force does. It pushes or pulls. It's pushing or pulling it up out of the page. If my current is going the other way, which it does, at the top it's going this way, at the bottom it's going this way, then I'm just going to flip my hand. So it was like this. If I flip my hand like this, now my thumb is pointing the opposite direction, okay, for the current, and when I do that, my palm is facing down. It makes sense that my force would be exactly opposite if I have exactly opposite current. Okay, does anybody have a question so far? So my force here is coming out of the page. My force here is going into the page. You need to think of it, this loop. I'm going to use an example. I'm going to use this tape. Guys, what would happen if I were to pull on this end of this loop? Pretend this is wire. If I was to pull on this end while also pushing on this end, because that's what the forces are doing. It's pushing into the page here and it's pulling out of the page here. What would happen to this? It would turn it. Look, pull, push. Pull, push. It's going to cause it to rotate. Okay, the reason I said this is an application of the right-hand rule, this is how a motor works. We're going to talk about motors later on, but a motor uses electrical energy, electricity, and turns it into motion. Okay, that force that is causing the motion of my loop of wire. It's going to pull it and push it, and it's going to cause this rotation. So when we talk about motors later on, we're going to talk about motors and generators and electromagnets and transformers and some other stuff. Okay, but this is really, you need to understand this so you can understand how and why they work the way they do. One thing I also want to mention, you'll notice I didn't bother labeling a force over here on this part of the wire. Okay, I do want to mention this because I said it the other day, and you're going to see something similar in the assignment today, so listen up. Obviously, in this part of the wire, if I were to label it, my current would be going this way, okay, because it's a loop. It's going to go like that. Guys, if your current is in the same direction or parallel to your field, when we talked about the right-hand rule, everything has to be at a right angle. I said think of this like an x-axis, a y-axis, and a z coming out of my hand. Everything's perpendicular. This is not perpendicular. Okay, if your flow of current is in the same direction as your field, there is no force at that point. You can't use the right-hand rule. In order to use this, things have to be perpendicular. Your field is perpendicular to the force, okay, because this one's coming up out of the page. This is a right angle formed right here. Okay, and then your current is perpendicular to your field. Field's down, this is this way or this way. Okay, but over here it's parallel, so there's no force over here. So just as a heads up, if you are ever running a current through a field in the same direction or parallel to the field, if it was going this way, that would still be parallel to the field, okay, then you're not going to have a force at that position. The other reason that you might not have a force is if you just have a stationary charge. We talked about this already as well. Okay, if you have a charge, and you'll see this in your assignment today, where the charge is not moving, there's not a velocity vector or there's not current labeled, if you just have a stationary charge, you don't have a magnetic force then either. Okay, you have to have moving charges, and the charges are going to have to be moving in a direction perpendicular to your field in order to have a force acting on that current carrying wire. Okay, so any questions about this one? All right, let's look at the next one, which you can already see it's drawn there, but let me go ahead and go on my screen. This is my force in, my force out. It's going to cause rotation. This one says indicate the direction of current flow through the wire. Okay, so again, I have my magnetic field due to these magnets, north and south. They're labeled here. I need to draw in my field lines from north to south. And again, I'm going to use my right-hand rule to determine which way the current is flowing. And obviously, it's a loop. So my current's going to go in one way and come out the other. It's going to turn around, okay, because it's a loop of wire. But we're going to use the right-hand rule just like we did a moment ago. So here is that example. Again, my field lines, I forgot to draw them here, go from north to south. So this is the direction of my field. So my fingertips are going to go like that. Okay, right now my palm is facing up out of my page, which is what this symbol means. And so in the bottom portion of my wire, where my force is out of the page, my thumb is pointing to the right, which means my current in this portion would have to be going this way. Okay, that would be the direction of my current. And of course it's going to loop around, and over here it's going to go this way. And I can see why, because again, if I flip my hand over, now my force, which is my palm, is going into the page, which it is, and my thumb is pointing to the left. So I have labeled my current to the left. So this loop of wire comes in and goes out on this side. Okay, but again, you're still going to have rotation because the forces are saying, hey, let's push in and pull up at the same time. It's going to cause it to turn. Questions about this? As I said, it's a more complicated application of the right-hand rule. And we're going to talk more about motors later and generators as well. But you will have a test question like this. Okay, I think it's on the quiz too. So you need to be able to tell me which way it's going to rotate, for example. Okay, the other thing we need to talk about is this. So this is also something new that we haven't talked about yet. The question at the top says, why do two wires with current in the same direction attract each other while two wires with current in the opposite direction repel? I'm already telling you what's about to happen. In this video clip, which is not loading in my screen, I'm going to open it up in YouTube instead, but in the video clip I'm about to show you, this circuit that this guy is using has a switch that allows it to be turned from series to parallel and back again. And the reason that's important is if you look at my diagrams here, in my series circuit, he's going to have these two wires going up. You're not actually going to see the top and the top right here. It's going to be inside of the apparatus. But you're going to see these two wires. And when it's in series, these two wires are going to be carrying current in opposite directions. It's going to go up and then it's going to come back down. Okay, and that it says up here that if it's in opposite directions, they're going to repel. So in the series circuit, we're going to see the wires move away from each other. In the parallel circuit, this is the same two wires, but now they are going to be carrying current in the same direction. And so they're going to attract each other. So let me show you the video clip and then we can talk about it a little bit more. Let's see, I thought I had it opened already. I don't know, whatever, I'll just play it over here.
Yours, global.edu.
Get past the ad. All right, so this is not the right one. I apologize. I thought that was the right video. It is not. Here it is. It went to the next video, that's why. Okay, so this is the apparatus I was just describing. These are those two wires right here. There's two of them side by side. When it's in series, they're going to be in opposite directions. When it's in parallel, they're going to be in the same direction. So right now it's not on, but he's going to switch it on. And here they are moving away from each other. And then when he turns it the other way, they move together. Okay, so away, together. And he's going to zoom in on it. But I'm sure you can see it. So again, when they're opposite directions, they repel each other. When they're in the same direction, they're attracting each other. So we're talking about the direction of the current in the wires. So let's talk about why that is happening. Okay, why are they doing that? So if we go back to our slideshow, okay, we need to think about what's happening. We already know that if we have a current carrying wire, that wire carrying current generates a magnetic field around the wire in a circle around the wire, right? We've done that already. We use this right-hand rule, the first one, where we kind of grip our hand in a circle and our thumb will go in the direction of the current. And so I know that if I have a wire carrying current, that it generates a field, and that field forms a circle around the wire. So I have two wires here. Each of them is going to be generating a field. The field that wire 1 makes is going to affect wire 2. The field that wire 2 makes is going to affect wire 1. And so we need to look at what those fields look like. And where they're affecting each other is going to be in the space that exists between them. Because again, the field's different directions everywhere. But at that point here, I've labeled it as Y and Z. We need to look at what the field looks like there. And guys, this is on your test. It was the most missed question last year. So if I were you, I would listen up. It says, based on the current flow shown in wires 1 and 2 below, determine the direction of the field in the shaded regions marked Y and Z. Okay, so we're going to use the right-hand rule to think about what this is going to mean for our field at Y and Z. So we're going to grip our hand like this. You can even hold a pen or a pencil if you need to. And I'm going to pretend that I'm holding wire 1 right now. Okay, when I hold wire 1 like this, right hand, it goes in where Y is. Girls behind it comes back out over here. I don't care about over here. Over here doesn't affect this wire. I only care about where Y is. And where Y is, my field is going into my screen. And the symbol we use for into the screen looks like this. So the field that wire 1 makes looks like that. And that field technically doesn't end right there. It's going to overlap with the other one. So it's going to overlap where wire 2 is, which I'll get to in a second. Okay, but so far so good. We okay with that? All right, we're going to do the same thing for wire 2, but again, this time I only care about this region I've labeled Z. Wire 2, my fingers again go in, behind, and come back out. That's what's happening here, they're coming out. So the field in this shaded region labeled Z is going to be out of the screen. That's the symbol for out of the screen are the dots. Again, these two fields are going to overlap. They don't end where they meet. They overlap each other, and they affect the other wire. Okay, so let's isolate and just look at wire 2 for a second. Wire 2 is now inside of the field that wire 1 made. That's wire 1's field, okay, the one that's going into my screen. We said that's what was happening here, and it overlaps wire 2. So because wire 2 is now a current carrying wire moving through a field, it's going to experience a force. We know that because of the right-hand rule. We're going to keep our hand flat and we can figure out what that force will look like. Okay, so again, my thumb needs to go in the direction of the current, which means my thumb is up. My fingertips need to go into my screen because that's what this symbol means for my field. And when I do that, my force is this way, to the left of my screen. Okay, so the force that wire 2 feels, wire 2 is going to be pulled to the left. So far, so good, hopefully. All right, now, but that's only 1/2 of it. Wire 1 is also in a field because wire 2 made this field that I had in orange. And that field is going to overlap wire 1. So let's look at wire 1 for a second. Wire 1 is in this field. Again, right hand rule, keep a flat hand. Thumb is up. Field comes out of the screen now. And when I do that, my palm faces to the right. It's facing where I'm standing. I can get it to load. It's not, I'll click it. Okay, and so it's going to look like that, which means wire 1 is going to be pulled to the right. Wire 2 is going to be pulled to the left, which means they're going to be pulled toward each other. That's what you saw in the video, was the 2 wires pulled together when the current was in the same direction. Now guys, the question you're going to see on your test, you don't have to do all that, because it doesn't matter whether the wires are both running up or both running sideways or into the page, it doesn't matter. If you have 2 wires carrying current in the same direction, they will attract each other every single time. I'm showing you why they attract each other, but that's not really the part that you're going to have to do. If you remember it, you don't have to do the whole right hand rule bit. You just need to remember that rule. So I would write down the bullet points on my screen, but if you want to know why, then you can look at the right hand rule stuff. Okay, but 2 wires carrying current in the same direction will attract one another. 2 wires with opposite currents will repel. So here's the 2 that are in the same direction. This is another illustration of it. Here's the fields generated. This field affects this wire. This field affects this wire, and it does so by causing them each to move toward the other. Okay, so the part of this that's a little bit tricky because it sounds backwards. We know opposite poles attract with a magnet. We know opposite charges attract with electrical charges. But when we're talking about the flow of charge in a wire, it's not the opposites that attract this time. That's why it's a little tricky. It's the current in the same direction that attracts, and it's because it's doing this. Okay, so again, don't get it mixed up. Wires carrying current in the same direction attract. If they were opposite, they would actually repel each other. Okay, that doesn't change the other rules we talked about so far. It's just a different one, and you'll need to remember it because it sounds backwards from what we've talked about. Okay, so again, if you remember this, you should be good. But if you don't remember it, you can do the right hand rule and figure out what would happen in any scenario, which is why I wanted to go over how to do it. Does anybody have a question about this? Okay, that is it for today's notes then. For the rest of the class period, you're working on the assignment 1203 magnetism problem set. You will find it in My Open Math. It is due by 11:59 p.m. tonight, but you should have plenty of time to finish it in class. Because we don't get out of here until 11:03, which means you guys have 22 minutes. So you've got plenty of time. As you're working through those questions in that assignment, obviously you're welcome to turn and talk to your neighbor, ask for help. Remember, you have random questions, so you're not going to have the exact same one probably. So make sure you're discussing, hey, how do I do this, and not, what'd you put? Okay, and again, this is due tonight. So if you don't finish it in class, it's homework. If you do finish it in class, I'm going to recommend that you work on the unit summary. The unit summary for this unit is no longer bonus points. We talked about that last week. Okay, it is just a PDF file. It's not even the same type of file, which we don't need the other type because there's no math. So it's really just definitions, multiple choice type things, and explaining why things are, or right hand rule stuff. Yeah. Okay, so it is still a daily grade redo, but it is no longer bonus points. I'm still going to encourage you to do it, guys. It has a lot of good practice in it. So especially if you need a daily grade redo, but even if you don't, it is a good resource. So work on 1203 first. If you finish early, you are welcome to get started or continue working on your unit summary. If you have questions, please let me know.